Good day! In this video, I am going to show that the subset whose elements are 1, -1, the imaginary unit I, and negative I of the complex numbers is a group under complex multiplication. So we have here the subset whose elements are 1, -1, I, and negative I of the complex numbers is a group under complex multiplication. So we need to prove this one. And we'll let G be equal to the set of 1, -1, I, and negative I under the operation multiplication. So in order for us to show that G is a group, we need to show these properties: closure, associativity, identity, and inverses. So for the first property, this just means that when we do the operation on the set of these elements, the answer is still in this set. So we have here the table in order to show that. We have 1, -1, I, and negative I. Then 1, -I, and negative I here. And the operation in this part. So take note that I is equal to the square root of -1. And this will serve as the reason why some of the items here is answered that way. So 1 times 1 is 1, -1 times 1 is -1, I times 1 is I, negative I times 1 is negative I. I guess I do not need to explain some of the items here. I'll just directly go to I times I times I is -1. Why is that? Because square root of -1 times square root of -1 is just -1. We'll just omit the radical sign. And negative I times negative I is -1 because negative times negative is positive. And then the square root of -1 times the square root of -1 is -1. And negative I times I is 1. Why is that? Because one of them will just become a negative number. So as we can see in the table, all of the elements are still found in the set. Hence, G is closed. Now, we know that associativity holds for multiplication, meaning the multiplication of the elements of G is associative. That is, AB times C is equal to A times BC for all A, B, C element of G. So, when we try to set values of A, B, and C from this set or substitute the elements on that one, despite of the order, the answer is still the same. So, we have already shown that G is closed and associative. Now, let us proceed. Suppose E is equal to 1 and 1 is an element of G. E here stands for the identity element. Then for all A element of G such that A times 1 is equal to 1 times A is equal to A. Therefore, 1 is the identity element of G. When we multiply any of these elements to 1, the answer is still the element. For example, 1 times 1 is still 1. I times 1 is I. Negative I times 1 is negative I. So, we have already shown that this meets the property of having an identity element. Next, for each A element of G, there is a B element of G such that AB is equal to BA is equal to A. Meaning, when we multiply an element from G to still an element of G, the answer is the identity element. We have 1 times 1 is equal to 1 times 1 is equal to 1. Negative 1 times negative 1 is equal to negative 1 times negative 1 is equal to 1. And I times negative I is equal to negative I times I is equal to 1. Thus, the inverse of 1 is itself, the inverse of negative 1 is also itself, and the inverse of I is negative I, and vice versa. Meaning, their inverses, the elements inverses, are still in the set. And that means that G, or the elements of G, have inverses. And we have already shown that G meets all the properties of for it to be considered a group. Therefore, G is a group. And that ends our proof. This is all for now. Good day once again.